Okay, we are recording. We are needing to go back here. All right, lecture 12. Okay, so before, and this isn't on the announcement slide because I found out about this about 5 minutes ago, but so there was an error on the exam 2 and the exam 3 grades on Blackboard that nobody told me about until today. So, yeah, they just told me. So. I'm sure you weren't. Yeah, I'm telling you, I don't know how that happened. You know, I was told that the changes to Blackboard were essentially just aesthetic, and while that's largely the case, I'm telling you, I feel like I'm that there's just little things that would. I normally operated it a certain way before, and now I'm still having to get used to it. Okay. I was a little behind on awarding like excused absences and whatnot and catching up with the attendance. Attendance should be up to date. A few of you got emails over the weekend where I said, you had an excused absence and I hadn't factored it into the grade book and it's factored now. So, and I think a few of you wrote back, but if not, just check your emails. We should be good to go. All right, let's talk about steel design. So, 2.6 is being graded, or at least it was as of yesterday. I haven't checked to see if that's graded yet, but 2.7 is due today. 2.8 is assigned today. You have 2.8 assigned today, due Wednesday. 2.9 is assigned Wednesday, due Friday. Now, Friday, we are going to have our exam review, and I'm going to post this 2.9 solution on Friday. So 2.9, I'm not going to accept any late submissions because I'm going to give you the solution right after it's due. And I'm doing that because we have our first celebration on Valentine's Day. So what we're going to do today is we're going to talk about block shear. On Wednesday, we're going to talk about threaded rod design, which I would argue threaded rods is probably the easiest thing, easiest concept on the first exam. And then exam review, and we celebrate. Sound good? Okay. One other thing, how many of you have attended the FE review session so far? I think there's only been one, right? There's only been one. Well, there's one today by yours truly. We're talking about statics land. We're going to do some statics problems tonight starting at 4 o'clock. Please feel free and come. Did somebody, is there going to be pizza?
Yeah.
I think there is. Okay, all right. It's like, who cares about the statics, right? Pizza, oh, that now we're talking, right? Okay, any questions? All right, if you are planning to come to the FE review session, one thing I would suggest, bring your FE approved calculator. Look, I'll admit, when I was in undergrad, I loved my TI-89, and then I had to push it away and adopt something like the Casio because that was all that was going to be allowed. So yeah, although to be honest, there is a reference manual, but I don't think it really helps that much with statics because statics, it just sort of is what it is. Okay, let's talk about block shear. I introduced this concept last time. Block shear is a connection-related failure phenomenon. It involves a combination of a shear failure and a tensile failure, and it is characterized by basically a chunk of the connection ripping out. And so it's sort of the final limit state that we need to address associated with tension members. Although, admittedly, we are sort of blurring the line between looking at tension members and looking at connection regions. So this is actually not listed in Chapter D that relates to design of members for tension. This is listed in Chapter J, which is the connection chapter. But we are going to talk about it here now because it's related to overall member capacity. So what happens in block shear, and really the most important thing to keep in mind, is that block shear is a combination of a shear failure path, one or more shear failure paths, and a tensile path. Okay, so the reason we call it block shear is because basically what it looks like in the end is that this block of steel, this sort of wedge of steel, sort of tearing out of the member. We're going to talk a little bit about how to identify potential block shear failure paths. I will propose to you that for this problem, that there are 2 failure paths associated with this problem, and there are reasons why you would check one versus another. I'd go ahead and tell you for this problem, I actually don't think that's the path that would govern. given the dimensions, although, dimensions would probably affect that. And if you ever have multiple failure paths, you just use the one that has the lowest capacity. All right, let's talk about the math. Okay, now I want everybody to turn to this page in the manual because this equation looks weird. I'll just tell you. It's on 16.1-138, and I'll just tell you, it looks strange. It's a weird equation because I want everybody to kind of see it. There are a few expressions in the spec that look like this. So this is on page 16.1-138, and this is the expression for block shear. So the nominal capacity is determined. Am I on the right page, 16.1-138? I think you're on 16.1-38. Did everybody see it? I think it's on the bottom, or is it on the top? No, it's on the top. It's on the top on the left side. So first off, the expression or the limit state is formatted similar to how others are formatted. We have a nominal resistance, and then we have a LRFD resistance factor and an ASC safety factor. So our LRFD phi value is 0.75. But then we got this, what's this hullabaloo going on right here? We've got the nominal capacity equals a pile of junk less than or equal to another pile of junk. Okay? And all that is the spec's way of saying that it's the minimum of those two expressions. Okay? So whenever you see an expression like this, that's what that means. So the nominal capacity according to block shear is the minimum of the first expression or the second expression. So that's what that less than or equal sign means. It's just sort of spec language for that. If you look at this expression, the expression in gray, so that's just me rewriting it a little bit, looking at sort of stacking it. You can see that there are a lot of similarities between the two expressions. So we're going to take this and simplify it quite a bit. So for example, we have Rn is the minimum of a pile of junk plus this, or a pile of junk plus this. And this term is the same on both sides. So I'm actually going to pull that out. And if you look over here on the left, both of these have a 0.6. So what I'm going to do is I'm going to take this expression and simplify it. So I'm taking this and simplifying it to that. Basically what I'm doing is I'm reducing the amount of repetitive calculations that I have to do. So I have Rn is UBS, FU, ANT, plus 0.6 times the minimum of those two terms. So let's digest this a little bit. So first off, let's look at that expression and see what's familiar. Fy and Fu, that should be familiar, right? Now, we haven't dealt with these, AGT, AGV, ANV, ANT expressions, etc. But we can probably guess what they are. AGV, the gross area in shear. ANT, the net area in tension. These are just gross and net areas, okay? Now, one thing that's worth mentioning is that if you look at the actual equation, you will not find an AGT term, right? There's an AGV, ANV, ANT, but no AGT. But how do you calculate a net area? What's the first thing that you need? A gross area. So we might as well list it because we're going to need it. Now, there's this UBS term, which I'll just go ahead and tell you, for just about every case we handle in this class, UBS is 1. That's pretty easy. And then our phi value is 0.75. So honestly, this really isn't all that challenging once you've identified your path. It's just a bunch of area computations. But I want to talk about some behavioral things. Notice this 0.6 popping up, this little 0.6. Do you notice how it's only multiplying the terms associated with shear? It's not adjusting the terms associated with tension. See how, like, rewriting the expression a little bit, you can see the 0.6 only affects the terms in shear. Right? You see that? Why is that? No, it is not a safety factor. I told you not to say it's a safety factor. Let's talk a little bit about failure criteria. Now, how many of you have already had soils? Or geotech, sorry, geotech. Already had it. How many of you are in it now? Most of you are in it now. Okay. You haven't talked about this yet, but you will. How many of you already had it? Okay, you have had. Did the more cool and failure criterion pop up? This.
Yeah.
Do you remember this?
Yeah.
Anybody remember? Okay, all right. For those of you that are in the class, you will see this at some point. What you see here on this image is what's called a failure criterion. Now, the reason I bring this one up is because you'll see multiple failure criteria during your time in undergrad. One of the most common ones that civil engineers deal with is the Moore Coulomb failure criterion. The Moore Coulomb failure criterion is an expression that works very well for brittle materials like concrete, like soil, okay? So the idea behind a failure criterion is this. You have an element that is subjected to multiple stresses, and so it is a means of determining whether or not the element will fail or not, right? So for those of you that have already had this class, you remember that you have your tau equals C plus sigma tan phi. That tells you the failure envelope. Tau is your shear stress. C is your cohesion. Let's see, phi is your angle of internal friction. Let's see, I remember something about soils. If C is 0, what type of material are you dealing with? Sand. There we go. All right, yeah. Sands are cohesionless soils. See, I know things about stuff. All right. All right. So basically what you do in soils is you're looking at a failure envelope of an element subjected to multiple stresses. And the idea is if it falls on one side of the envelope, the element is safe. If not, the element is unsafe and you need to do some redesign. This failure criterion would not work, however, for steel. All right, I bring this up just to relate it to something that you're going to see in another course. But it wouldn't work for steel because for steel is a ductile material. It doesn't behave the same way as a brittle material does, like soil or concrete. So we need a different failure criterion. We need the most common failure criterion that we use for metals or ductile materials is what's called the von Mises yield criterion. Now I have an equation for this in 2D. The equation for 3D is a little bit longer. It's not harder, it's just longer. But basically what you're doing is you're comparing the yield stress in 2 dimensions to what's going on under this square root. Now I want to pay attention to this from a mathematics perspective. Let's say I'm taking a piece of steel and I'm yanking on it, and that's all I'm doing. I'm applying a normal stress. So if I apply a normal stress, let's set everything else equal to 0. So if I set that equal to 0, that equal to 0, that equal to 0, so that's going to go to 0 as well. I'm going to get the square root of sigma x squared, or sigma x equals Fy. And what that's basically saying is, if I take a piece of steel and I yank on it, it yields when the stress hits Fy. Yeah, of course, right? That's what the yield stress is, right? But where the benefit is, okay, this will tell us where an element of steel will yield if it's subjected to multiple stresses, if it's being stretched and stretched this way and sheared, okay? Now, what I want to talk about is this right here, this 0.6, okay? Now, this 0.6, I propose that it's only showing up with terms associated with shear. So what happens with this equation if I only have a shear stress, not a normal stress, but a shear stress? Well, what happens? Well, if I set all the normal stresses equal to 0, but I leave the shear stress, apply only a shear stress, that goes to 0, that goes to 0, that goes to 0, that goes to 0, and I'm left with that, or that. Does that make sense? So what we're finding is that if I set all the normal stresses equal to 0, I propose that the steel will yield when the shear stress equals Fy divided by the square root of 3. Now, what is 1 divided by the square root of 3? Well, 1 divided by the square root of 3 is like 0.5774, and so the steel spec says, let's just use 0.6, okay? So it's not a factor of safety. That's not what it is. I propose that steel will yield under shear when the stress is about 60% of the yield stress. So it's not a factor of safety. It's reflecting what's actually going to happen if you take an element and subject it to shear. If you wanted to apply a factor of safety, you'd have to apply it on top of that. Does that make sense? So that's why this is not the only time we're going to see 0.6 built into the spec. And when you do, you look, and you'll see it's always related to something subjected to shear. The steel spec, or the building spec, uses 0.6. If you actually open up the bridge spec, you'll see 0.58. Like, for example, for shear capacity of webs. So, any questions? Yes?
So, like, I understand that it's not like a factor of safety or anything. It's just the proportionality of, like, the yield point of shear versus tension.
Yes.
Okay.
So, here's the best way of describing it. Okay, 0.6 times 50. That's what, 30? Okay, so if I have grade A992 steel and I yank on it, it will yield when the stress is 50 KSI. But if I take grade A992 steel and shear it, it will yield when the shear stress is 30 KSI. Because it's in shear, not because, I'm saying that when you take a ductile material and apply shear to it, it's going to yield at a stress lower than FY. It's not a factor of safety, it's a reflection of reality. That's what I'm saying. This is good stuff. Any questions? Okay. Now, one of the things I sort of skipped over was this term UBS. UBS is kind of like a shear lag factor for block shear. It's very empirical, and I want to talk a little bit just sort of on the side about empirical expressions. Empirical expressions are intended to simplify very complex behavior in the real world. The more elaborate your equation, the better your accuracy is going to be. But there is a point when the line between complexity and simplicity gets a little blurred. I mean, I guess my point is, if we really develop some super complex expression for this, would it really affect real world designs? You know what I mean? So there's a point when, let's just use an empirical expression, even if it's a little inaccurate. As long as it's good enough to reflect the behavior, then we're good. Now, the only time that UBS ever doesn't equal 1 is whenever you have what's called a coped beam. So a coped beam is when you have a floor system. Let's say you've got beams framing into beams, right? So let's say you have an I-beam right here, and you have another I-beam that you want to connect, right? But you want to connect it such that the floor system is flat. Well, what you do is you say, all right, I'm going to take that floor beam and I'm going to cut a little bit off the ends so that the floor sits flat. Does that make sense? That process is called coping. So if you ever look at floor beams framing into floor beams, you can see it in the old engineering building on the other side of the canopy. If you look at those floor beams up on the roof, you can see floor beam connections like this. That's called coping. And whenever you have multiple rows of bolts along a cope, then you use UBS as 0.5. Other than that, you use 1. And so we're not going to deal with any of those types of connections in this class. So we're going to use UBS as 1 for like every problem. So everybody okay with that? Okay. Let me, so that I don't get that little warning. Okay. I want to talk about identifying block shear failure paths. So do you remember the lead line? Remember me talking about that? How do you define the lead line? Somebody. The lead line of bolts.
Like the ones that are squarely break first.
So, but okay, so here's the tension member. I yank it and I fracture along the lead lines. What can you tell me about all the bolts after the fracture?
Basically untouched.
They remain intact, right? Remember that? So the lead line is the line of fracture such that if fracture were to occur, all the bolts would remain intact. Does that make sense? Everybody okay with that? So how do you identify block shear failure paths? Well, in order to identify a block shear failure path, you need to leave all the bolts intact. You need to actually separate the member from the connection, and you do actually need to include a path subjected to shear. So I propose that these two paths could potentially occur for block shear. So I want to look at this path over here on the left and this one on the right. Then I want to ask you, which one of these do you think would govern? So this path over here on the left, I've got this path right here. Is it subjected to shear or tension? Shear. This path over here, shear. And this path, tension, right? So this has two shear paths and one tensile path, right? Now what about this path? So I have this shear path right here. Would you agree that these shear paths are basically the same? Did everybody see that? So let me ask you a question. So if we're looking at shear, this has less area than this does, right? Let's say this is like 5 inches, right? Here I got to rip through 10 inches of steel and shear. Over here I only got to rip through 5 inches, right? So it's a lot less material to rip through. Now, I do have more material to fail in tension, but all things being equal, which do you think is the weaker path? The one on the left or the one on the right? Which do you think has the lower capacity? The one on the right, right? This is actually ripping through less steel. Does that make sense? Now, you could argue that there is maybe a third failure path. So there's this one on the left, this one on the right. Well, what about just this one and ripping that whole chunk over there on the right, like ripping all of this out? But then there's no shear. That's just net section fracture, right? That's not block shear, right? Does that make sense? Everybody okay with this? All right. I got a little inventor happy, so I want to show you something. Where'd my mouse go? Hold on. There we go. All right. So this is Inventor, okay? And what I did is I created a couple of connections, right? So here's an angle, and that angle has, you can see here, 8 bolts. And I tried to draw this somewhat to scale. This has 8 bolts through one leg. And I want to sort of convince you that this is really the only failure path that you need to consider. For example, I would argue you do not need to consider this, right? Because that's a lot of additional area in shear, right? I also would argue that you could say that the failure path goes like that. But then you would have to rip out all of that material through the angle. Does that make sense? See, I'm thinking that this is really the simplest failure path. And I think what would happen is that it would separate kind of like that. Does that make sense? So does it make sense that it's easier to fracture along this path than it is through all of that material right there? Does everybody kind of see that? Okay. All right. So I've got, this is a good example of an angle. Here's an example of a channel. So here I have a channel, and I argue that this is really the only feasible failure path, because other failure paths, like I could say, well, what if I just rip through all of this? But yeah, then I got to rip through all that material right there, through that little fillet and that bend right there. That's a lot of material to rip through, right? So really the only failure path is this, and what will happen is, hold on. Is we would just rip that part out. And again, notice what's happening at the end. All of these bolts would remain intact. We're not shearing any of the bolts because the member that's ripped off, keep in mind, here, let's move that out a little further. The member that's ripped off, so imagine that channel separating, it's not taking any bolts with it, right? Does that make sense? I mean, yeah, you might think, well, that's ripping around a little bit. Yeah, that'll get deformed and just sort of chug out. Does that make sense? Okay. Now another one that I think is a little wild is this right here. This is a wide flange. So this is a wide flange connected via the flanges. And really the only failure path that makes sense is this one right here, right? Because any other failure path, you'd have to rip through all of this, all that material through the web and through the central part of the flange. That's just a lot of material to fail through, right? But when you compute capacity, you got to be very careful, okay? The way that I compute capacity for these problems is I say, let's compute the block shear capacity of a single block, and then let's multiply it by 4. That makes sense? So that reflects the entire capacity. So take the block shear capacity of a single block, multiply it by 4, and then don't forget your phi value. That's an easy thing to forget at the end, is phi is 0.75. Does that make sense? Any questions? Let's do a problem. All right, let's do a problem. So I have an angle, a 6 by 4 by 5/8 of A36 steel, and it's going to be used as a tension member. Now I really upped the bolts on this one. I used 1-inch diameter bolts. I got a little nuts with them. So we're going to determine the design capacity of this member according to block shear. Yes, sir?
Does block shear happen staggered?
That's a great question. So the question was, does block shear occur on a staggered bolt path? So the short answer is it could. The longer answer is whenever you're looking at your gross area and net area in tension, you would just include your staggered paths. Now let me give you the other addendum so that you're aware. Because here's the real question. Are we going to have to do that on a homework or an exam? No, I'm not going to make you do that. Because you're like, I've been around the block long enough. I know there's the question and then there's the real question, right? The real question is, do we have to worry about this on a celebration? No. So, but yeah, so what you would do is if you had like a staggered bolt path here and you're computing that net area, just include the stagger factors. So that's how I would do it. So. All right, I'm going to give everybody a sec to chug into this a little bit. And then we will start doing some work. Now, as you're writing this down, I want to make sure that everybody has a good 3D view of what we're looking at. So here's the angle, and what I'm suggesting we've got is sort of like this. Let's see. And we're dealing with this. Does that make sense? So can everybody identify sort of conceptually the block that we're going to be ripping out? So it's going to go like that, right? Does that make sense? Okay. All right, let's get some seed values before we start chugging into this. So Somebody tell me what Fy and Fu is for this material? Hopefully by now you're starting to sort of remember this stuff. What's that?
50 and 65.
No. A36 steel.
36 and 58.
There we go. 36 and 58. He's looking to the person next to him like, you told me it was 30, 50, and 65. What's that? All right. One other thing, well, two other things. One, we know that, okay, so bolt diameters, or no, let's call it hole diameters. So what's the effective hole diameter? 1.125, right? Goodness, I thought I turned that down. All right. And finally, we're going to need a thickness. What's the thickness of the material? 5/8. Okay. Okay. Everybody with me so far? All right. Now, so let me close this because I didn't open it. So are we all in agreement with this that here's the member and we're ripping through this, that this is our block path? Is everybody okay with that? Okay. So let's investigate this path a little bit. All right. This path, is it experiencing shear or tension? This path, is it experiencing shear or tension? Okay. Okay. Now, let's compute our 4 areas. Now, we're going to start with the shears. Okay? So, AGV. Right? We're starting with the gross area because how do you compute net area? You first need the gross area. So, I need the gross area in shear. How long is this? 10.5 inches. Is that enough for an area? How do you compute area? Length times, huh? Well, yeah, but what is the width in this case? The thickness. And what is the thickness? 5/8. So, because here's what's going on, right? Right? Here's the angle. Right? And so if we're talking about this block, this is the area that we're talking about in shear, right? That little shaded path right there. And so it is the width times the thickness, right? So okay, is that making sense? Is everybody okay with that? If not, I mean, please tell me. What is that? 6.56 square inches. Do I have a second on that? We'll call it 6.563. Okay, now let's do the net area in shear. Now, let's just keep this simple. What's the general definition for the net area? It is the gross area minus the area lost due to the presence of bolt holes, right? So I propose that it is the gross area minus some amount of holes. We'll get to that here in a bit. But the amount of hole, or the area of a hole, is the diameter times the thickness. Is everybody okay with that? Now, how many holes do I subtract in shear? You're saying 4. What'd you say? 3.5. Interesting. That's correct. It is 3.5. Because, look, here's the path, right? So, 1, here's a hole, 2, 3. That's not a full hole right there. That is only a half a hole, right? So it's not 4, it's 3.5. This is 3.5 holes. Does that make sense? So what is this? Say it again. 4.102. Do I have a second on that? Because everybody brought their Casio FX 115 or ES Plus or similar scientific calculator. Is that correct? Do we really have to get it out? Yes. All right. AGT, remember, AGT is not actually in the block shear expression, but we need it because we need ANT. So somebody tell me how to compute AGT. What are we going to take? It's the thickness times what? And what is that width? Say it again? 3 3/4. This is 2.5. This is 1 1/4, so that's 3.75. So what do you got? 2.344. Do I have a second on that? Everybody good? Now, if that's the case, all right, let's see if everybody's paying attention. So ANT is again going to be AGT minus some amount of holes. How many holes are we subtracting for the tensile failure path? 1.5. See, once you see the shear one, the tensile one's super easy. Okay. So what do we got here? Everybody brought their Casio FX 115 ES Plus or similar scientific calculator. Is that correct? I had a 96 on the second exam. I didn't think I needed to bring my calculator. And the third exam. 1.289. Sound good? Okay. And note, UBS is 1. How we're doing on time. We're doing good. Okay. Sound good? All right. So let's walk through the expression because this is kind of new, but it's really not that bad. Okay. So the block shear expression is as follows. So that's the equation. Kind of a mouthful, but it's really not that bad. Basically, all we're saying is that the capacity according to block shear is our tensile capacity plus our shear capacity. And what we're saying for shear capacity is that we got to adjust by 0.6, and that it's the minimum of either shear yielding or shear fracture. That's basically it. Okay? So, again, the equation looks like a mouthful. It's really not. Okay? Now, before we start chugging out stuff, let's just fill in all our values. Okay? So, this is 1. This is 58 KSI. This one, A and T, is let's see. Now, before we start doing any chugging, let's just fill it in. Okay? All right. Now, somebody help me out. We're going to take it one step at a time. What does this yield? When you check that out, what do you get? Just this part.
74.762.
So we'll say 74.8. Okay? All right. Let's do each line. And again, you could probably do this a lot faster on a homework or an exam. I'm just taking my time with it just to make sure that we all follow what we're doing. All right, so what's 36 times this? Wait, what? So 236.3. And what about the second one? All right. Is that okay? So we'll say 74.8 kips plus 0.6 times the minimum of those two. The minimum of those two is that. And so what does that yield? So 216.6. Is that the answer?
No.
I forgot something. I forgot the phi value. This is Rn. So Rn phi Rn is throwing the 0.75 on there. So what does that yield? So we'll call it 162.4. What do you think? So that's the design capacity according to block shear. Now, one question that I do get is, does this matter? Let me ask you a question. Watch this. note, hold on, I closed it. See, what do we have? We have an L6 by 4 by 5/8. When you chug this out, so an L6 by 4 by 5/8, you can look up the gross sectional area or the cross sectional area. 0.9 FYAG, when you chug this out, is 189.9 kips. What does that mean? Now I didn't compute net section fracture. I could, but what does that mean? At a minimum, the block shear could govern, right? Because net section fracture might be like 150. You know what I mean? I don't know. I haven't done math, right? But the point I'm making is that it could govern, right? It could. Now, I want to talk a little bit about design decisions, and then we're going to call it. So, do you ever need to account for block shear in the design phase? No. We have a procedure for design. We factor the loads. We determine AG design and R design. We pick a member. We check net section fracture. We check our efficiency, right? Now we've got this block shear limit state. What do we do with it? Well, I propose it's not something we need to incorporate in our design phase. We just need to, it's another check at the end. Now, what happens if block shear governs? There's a couple of things that we could do as designers. We could pick a bigger member. That might fix it. What's another thing that we could do as designers that might improve block shear capacity? Add some more bolts. There's another simpler one. What's that? Well, that's no, because that might make our shear path and tensile path shorter, right? And we might need those bolts. But what about taking this 3-inch spacing right here and making it 3.5? Just space your bolts out just a little bit more, you know? Bump that shear path up just a little bit, you know? That's a simple fix, right? Another fix is maybe to add another 2 bolts here at the end. Make that shear path a little longer. That's another possibility as well. But I want you to think, I just want you to keep in mind that the answer doesn't have to be pick a new member. It doesn't have to be that. You can change your connection geometry a little bit and bump up the capacity that you need. Usually, if block shear governs, it's not by a ridiculous amount, and you more often than not can tweak your connection geometry around and get it to work. Maybe you need to bump up your member size, but you know, I think you get it. Yes, sir.
Even if it does govern, what if it's like still above your
PU? Yeah. That's fine. It can govern, but that doesn't mean your efficiency is over 100% either. That's a fair point. And keep in mind, there are yet even more limit states we haven't talked about. What if none of these limit states govern, and we're actually governed by whether or not the bolts snap in half? We haven't talked about that yet. We will talk about that after the first exam. So, sound good? All right. I will see you on Wednesday. On Wednesday, right? That's the next day of class.